All right, hey everyone, welcome back. We're at 2:30 now. So we're going to go into our intro to feature engineering. Before we do that, can we just get a thumbs up to see who's back? All right, awesome. So we got a good amount of thumbs up. We'll just do a little intro to just give some people some time to get in. So basically, in a second, I'm gonna pass it off to another one of the senior directors in the education portfolio, Eric, and he's gonna go through his presentation on feature engineering. Followed by that, we're going to basically talk a little bit about the competition, and then hopefully right at 3:30, the competition will be made available for you, and then you'll have about a 5-hour time slot to do it. So Eric, you should be good to share your screen when you're ready.
Yep. Can everyone see my screen?
Yep, you should be good. All right, Eric, floor is yours.
Right. Yep. Thank you. So welcome to the last presentation of AI Oasis. I'll be talking about feature engineering, and I guess the way the workshop will go is I will first present my slides, and then I'll move on to a notebook with more concrete examples. So feature engineering is kind of a catch-all or an umbrella term for basically just any transformation, any manipulation of our data to characterize a problem. So when we have data, we often kind of overlook it. We don't really think about processing our data more, but anything from just revisualizing our data, processing it, cleaning it up, making new features, all these, they really help make our models better and make our models perform better because as everyone knows, and as everyone probably has heard, garbage in equals garbage out. So if your data is good, then your model will be good. And your model basically all is determined by the quality of your data. So this workshop kind of focuses on how the three major components of feature engineering, and these three major components kind of help deal with how to make our data better and more, I guess, more readily accessible for our models to use and interpret and find trends in. So I'm going to go over each of the three components. So there's a feature extraction, feature generation, and data separation. And I'll try to walk through all of those by the end of this workshop. So fundamentally, feature engineering is basically a representation problem. And what that means is we always got to ask ourselves, what data is kind of best represents the solution for our problem. So we want to always look for the data that kind of encapsulates a problem, kind of represents the entirety of the problem. And by analyzing that data, we can basically find trends and find a solution to what we're looking for. So, and obviously in these cases, depending on the problem we have, depending on the what we want to solve for, some data might be good and some data might be bad. So it's all up to basically us to try to figure out what data is good, and we pick and choose and we transform this data. So in this workshop, I'll try to the example will be the fruit classifier 9000, where we'll just try to classify different types of fruits like oranges and apples, and then we can see how feature engineering will work. So to start off, I'll talk about feature extraction. So for feature extraction, we're just picking and choosing what features best represent the problem we're looking for. So for example, if we have a classification problem where we want to distinguish between apples and oranges, we want to see that obviously they're both fruits, so that's not a really good feature, and they both grow on trees. So obviously, since those features are similar, then we can't use that to distinguish between the two. But we see that if we distinguish them based on their color, if we choose that feature, then we see that we can easily find the difference between an apple and an orange. But take, for example, if we want to try, instead of looking and classifying between two different fruits, we wanted to see between fruits and vegetables. So then obviously the color feature we used before won't work because there's a multitude of colors of different vegetables. So then to classify it, we can use a feature that didn't work for us before, which was that apples and oranges are fruit, whereas vegetables are vegetables. And then we can use that feature to better represent the problem we're trying to solve. So then another example is, instead, what if we have two fruits? So we have an orange, an apple, and a pumpkin, or multiple pumpkins. And I did search it up, and pumpkin is a fruit, by the way. So in this case, well, we realized that we need more than one feature because some features may be the same for some data points, and then some features may be different for others. So by combining these features, we're able to basically solve this problem. So in this example, we need to use two different features: the fact that oranges and apples grow on trees, whereas pumpkins grows on flowering plants, which are kind of low on the ground, as well as the color of the apples, oranges, and pumpkins. So then one very important thing I want to highlight is that when we're looking for these features and when we're extracting these features, as I mentioned before, not all features are like good, like they're good in some circumstances and good in others. But one important thing is you want to make sure that you pick features that are related that really represent the problem you're trying to solve. So for example, in this case, we could easily just say that an orange has no leaf in the picture on the stem, whereas the apple in the picture does have a leaf. And this seems like a great piece of data, a great feature that we could use to distinguish between the two. But in actuality, that like leaf doesn't matter. It just depends on like the picture that was taken, the picture I put in the slide. So make sure you're always choosing the right features. And in the notebook, I'll show like some kind of ways to pick and choose the features you want. So next up is feature generation, and feature generation is basically what we do is we look at our previous features and we want to kind of generate new features from the existing features. And the reason why we want to do this is twofold, or there may be two different reasons, but the first one is we might have too much data because sometimes like obviously sometimes having a lot of data is good, but in other times you want to be able to cut down on the computational time that you're trying to train your model for, because you don't want to like leave your computer running the entire night and fry it. And in some cases, like the quicker it is, the better. So if we are able to look at multiple features and try to like maybe condense them or squish them and like summarize them all with one feature that kind of basically represents everything we're looking for, then obviously that is way better than having all these features present and fed into our model for the data. So for example, we have an orange, and it could be all these features could be it's a fruit, it's orange in color, it's sweet, it has seeds, it has peels, it has stems, it grows on trees, etc. But as you guys will see in the next slide, there's one easy variable I can use to or one easy feature I can use to condense all of the information together. And one other very important aspect is that sometimes our data isn't descriptive enough, and there's some like hidden trends that we're able to like maybe pull out if we use if we kind of combine our features together and or generate a new feature. So an example here would be if we looked at like time series data. I'm sure everyone kind of has heard about time series data where sorry, it's sorry, it's formatted in years, months, days, maybe hours, minutes, seconds. If we look at something like that, it's kind of hard for the computer to realize like or try to look at the trends within the data since they're all just in this format. But if we want to look at like maybe in this example here, if we want to analyze like the trends of people like nightly outings, and we want to see like when people go out at night the most, we can instead transform that time series data into something more manageable and something more, I guess, representative of what we're trying to look at. So we can transform our time series data into just the day of the week. So Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday, so on. And because of that, we can see that we indeed do see a trend that most people would go out on Friday and Saturday, whereas that'd be kind of impossible for our model or for the AI to realize just through looking at like the dates of like the years, the months, and the days. So the example I wanted to show is that if we try to we can generate a new feature. In this case, I'm just generating a feature that's being called like the family of fruits. And with this family, it kind of encapsulates all the data that we looked at before. So in the citrus family, we know that orange is part of it, and orange is a part of it, and it's a fruit. It grows on trees. It's sour. It has a peel and a rind. And by like generating this new feature, by looking at all of our previous features, we can easily cut down on the time that the computer requires to process all this information and all this data. And I've done that respectively for all the other two fruits. So the apple, which I believe is the apple family, and then the pumpkin is part of the squash, which has like kind of a potato-y consistency. I'm not sure if anyone has eaten a lot of squash, but yeah. So now lastly, I want to talk about data separation. And for this, what happens is sometimes our data is not in a really like easy to analyze format. Sometimes it's kind of tangled up. It's hard for us to interpret. Or maybe sometimes what happens is like we as humans were able to interpret some sorts of data, but when we feed it into our model, when we feed it into the machine, like the computer based on the algorithm, it's pretty hard for them to distinguish between what's one case versus what's another case. And if that's the case, then we can't really, it's harder for us to analyze the trends in the relationships and analyze the patterns, and thus our model cannot perform as well. So what we do in data separation is we try to revisualize, or we try to transform our data into like another form, an easier to digest form that we can analyze and it's easier for the computer to analyze. And this, by transforming it into this easier to analyze format, then it's easier for the computer to look at the trends in the data and figure out and separate between the two cases. And in this example on the right, we see that in the first graph, we see the data basically placed in a circle. And we see that obviously to us humans, it's easy to see, but for the computer, it's really hard for them to distinguish between the two. And I'll touch more upon that in the notebook. So here's just a summary before I go into more in-depth concepts on the about feature engineering. So there are three main ideas of feature engineering, which is feature extraction, feature generation, and data separation, as I touched upon in the slides. We want to make sure that every time we have data, we at least do some aspect of feature engineering. So on the top of the flowchart, when we get our data for our whenever we're making a model or when we're training something, we want to make sure we try to look at the data and we try to just like find ways to make our data easier to manage, easier to easier to digest for the computer. And we do this by feature engineering. And you don't always have to use all three aspects of feature engineering, but just make sure to keep all three in mind whenever you're doing any project related to machine learning and data analysis. And as always, we know that good data equals a good model. It might seem like very like early on in the process, but if you make sure that your data is good, it'll pay off down the line when your model is rewarded by better accuracy and better reliability. So now I'm gonna hop into the notebook. So once again, the format of the notebook will be similar to the one in the workshop, but I'll do it in a different order. So I'll start first with feature separation. So I think I can just gloss over some of these imports, but what we wanna do is, or we just want to look at, I've already generated the data. So this is unrelated. In the real world, everyone will have like data that they got from somewhere else. I just generated mine. But what we want to do is, in this example, we see that we can plot, let me make it bigger. We can plot this graph, this scatter plot, and we see there are two cases in red and in blue. And it's easy for us like right now to see that it's pretty easy to separate because all we can do is we can draw a line at y equals maybe 45 along the y-axis, y equals 45, and that can easily separate between the top case, which would be all the data that's above the value 45, and then we can separate it to the bottom case as well, which would be all values below 45. So this is an example where we don't need to do that much data separation. It's like already pretty well separated for us. So I just draw a line up, like a simple blue line to show how we would separate the two cases. So then I generated another example. This is just the data I generated, so you guys can ignore that. But in the second example, before I start, I just want to kind of give a refresher on how polar coordinates work, just for like if anyone is rusty. So in terms of looking at polar coordinates, when we usually look at graphs from like all the way since like grade 9 or or like middle school, it'll be presented in the form, sorry, my voice. It'll be presented in the form of X and Y. So we would just basically, if we want to plot these points, we would just look at the x-axis, draw a line up, and look at the y-axis, draw a line across, and then where the lines meet, that's where we would plot our points. But in polar format, it's a bit different. So when we look at each point, it's kind of a point on the circle, and it's plotted by the first value is the radius of the circle, and the second value is the angle theta. So for polar coordinates, what we do is we look at like the angle of radius r, and then we just basically move in that number of degrees to the left of the from the x-axis, and wherever we hit that angle, that's where we plot the point. So for example, in this we have a circle of radius 6, which you see in the picture, and then since the angle is 45 degrees, once we hit the 45-degree mark, that's where we plot our points. So after that polar coordinates refresher, here's just the data I showed before in the workshop. Something I want to mention is it'd be kind of hard for us to like draw a line across all of the data points like I did previously with the scatter plot with y equals 46, because if we try something like y equals 0, then it's hard for us to separate between the two cases because it's like a 50-50 split between the cases on the top and the cases on the bottom. If we try something like maybe like a diagonal line, we'll be able to classify some of the cases in blue, but we'll also have a lot of the cases in red, in orange, which is hard for the machine to distinguish between the two relationships. If we have something like, maybe if we tried to define something like, if we made a parabola, like right between the intersection of the two circles, then we'll obviously, and we define that everything above the parabola between these two circles will be case one, and everything below will be case two. We can indeed, like, we'll get a better accuracy of the, we'll get all of the cases in blue, but we'll also get a lot of the cases in orange that are above the parabola. So like whatever way you try to see it, like it's really hard for us to just try to extract the data in this format, in this Cartesian plot format, because it's just like, unless you do some complex mathematics, it's really hard to like make like a circle bounding box that only takes the values within the blue and then takes all the values outside of the circle as the orange. So instead, what we can do in this data separation component or topic is we can just plot it in a different way. So we can plot it in terms of a polar coordinate system. So what I mentioned earlier with the y-axis and the x-axis, in this case, the x-axis would be the radius of the circle, and the y-axis would be the degrees. And in this case, it'll be radians. So in this way, we can see basically the data is a lot more separated. And if we look above, we see that since the radius is on the x-axis, the smaller circle will have a smaller radius, and thus it'll be on the left. And then the bigger circle and the orange will be on the right because it has a larger radius. And that's all that we use to define it, because the radians, it doesn't really matter since it's in a circle. We can just define it by the radius of the two circles. And this way, it'll be easier, much easier for the machine to analyze the trends in these two patterns, because then it's easier for us to like quantify to our models that this is how they're different. One has a larger radius and one has a smaller radius. And I just put a simple line at radius 4.75. So any points that have a radius less than 4.75 will be considered case one, and any points that have a radius of larger than 4.75 will be case two. So now to talk about the rest of the two, the feature extraction and feature creation, I'm actually going to bring on another data set from Kaggle. So this data set is a student performance in exams data set. It's a completely fake data set. It's just used to, I guess, like allow people to play around with the models and stuff. So it's completely fake. It's not actual student test scores. But so here's just the data that I printed out. We see this table. The labels that are used are the math scores, the reading scores, and the writing scores. And then I just want to highlight the features that I'll be referring to are all of the features that are not the labels. So these features just kind of describe each student and describe the data points we're looking at. So these features would be like gender, race, parental level of education, the lunch, which would be like if the school subsidizes or basically gives a lunch for free, or if students have to bring their own lunch, and if the students have taken test prep courses or not. So when I'm referring to features, I'll be referring to all of these features within the table on the left side, and all of the labels will be the scores that we're looking at. So now I'll be talking about how we can extract features from this data set. So for example, if we wanted to look at like only certain features, because we determined that like maybe depending on a problem, if we think that we only want to analyze like features because of what we're looking for, or if we just see that some features are like useless to our data set, then we can extract those specific features and just only look at those features and plug those into our model. So for example, what we want to do is maybe we want to look at maybe just the effect that a subsidized lunch, like if the school subsidizes the lunch, what effect that would have on the test scores. So what we do is we basically just create another data frame where we only take the feature lunch feature, and then we also take the all the score labels, so the math, reading, and writing score labels. And then I just printed the table over here, which shows that we only are looking at the lunch and the rest of the scores. So to analyze this, what we can do is we can separate them further into two data frames. We can have one data frame that's only the students that have the subsidized or free lunch provided from the school, and we want to analyze those the scores of those students. And then I also separated another one, which is just students in schools that have standard lunches, so they have to bring their own lunch or they have to buy their own lunch, and we want to look at those scores separately. So what we can do is we can basically just combine all of the average values. Oh, this is more for illustration purposes, but we want to just combine all of the values for the two different data frames, the two different students, either the ones with free lunches or with lunches they have to bring by themselves. And we maybe just want to look at like their average test scores in the 3 sections. And all I'm doing is I'm just gonna like average all of the students together in the 2 cases, and we'll just plot that, and we can see that with feature extraction, this is the plot that we see with the effect that a lunch has on our 3 different scores, so math, reading, and writing. But this graph is only for illustration because in an actual case, you guys will just extract all these features from each student, and then you can just plug that feature into the machine learning model, and then that'll help you calculate what you need, or that'll help you train your model. So lastly, I want to kind of talk about feature creation. So feature creation is kind of something that's like not really looked at because it's very niche. Like there's only certain times you want to look at or you want to use feature creation. But basically with feature creation, we want to just create new features that can help shed some light on our data or problem, or it can reveal a new perspective on our data, or kind of reveal a hidden relationship, or it can help us conserve our computational capacity, like I mentioned before, by reducing the amount of data points, or sorry, not data points, by reducing the amount of features we have for each data point. So for a complete hypothetical, this is just a hypothetical situation example that I'm using. Let's say, for example, we wanted to create a new variable or find a new perspective to look at our data set. And we want to see if there's like a relationship between a parent's education, the student's parents' education, and their test preparation courses. So we want to see if there are more students that will, if there students that have a parent with a higher education, if those parents will push their students to sign up for these more test prep courses. And we hypothesize that if a parent has a higher education level, then they might like place a greater emphasis on academic performance or learning or like doing well in school, because since they themselves have a higher education, maybe they just place more value in doing well in school, and that reflects within their children as well, so the students. And to look at this, we'll see maybe if they do place a higher emphasis on these academics, then they'll try to push their children to sign up for more test prep courses. And we can call this new variable that we're looking at parental influence. And we want to see if this parental influence variable kind of has a different effect or kind of reveals like a hidden relationship within the data set. Oops, I accidentally. Okay, yes, sorry about that. But what we do is we once again extract those features that we want. So we want to just see the parental level of education and test prep courses that we look at as the features. And we want to see, we also want to include the labels that we're using. So the math score, reading score, writing score, and see how those stack up with our new feature. So just to define our new parental influence feature, all I'm going to say is that if the parents has an education level of master's or above, then and the test preparation course is complete for the student, then we can say that there's a lot of parental influence on that student. And then likewise, if the parents' education level is maybe like bachelor's or so, then and their children have completed their test prep courses, we can say that there's only some parental influence. And as we trickle down, if their parents' education level is associates or some college, we say that maybe there's a little parents' influence that they want to push their children to sign up for these courses. And if we say that if the parent just hasn't completed high school or has completed high school, then there's no parental influence. And if the students have not signed up for test prep courses, then we can just say that there's no parental influence. And all we do is we basically, in this piece of code, all we're doing is we're just assigning those values and we're assigning them into a new column or a new feature called parental influence. So now lastly, what we want to do is we want to just visualize our data in a real life scenario. You wouldn't have to visualize your data. This is just for illustration only. You could just feed this new variable into your model and see if you get a better performance or a better accuracy. But let's say we wanted to look at the how the parental influence affects students whose parents have a bachelor's level education or maybe associate's level or some college level. So all we're doing is we're creating new data frames where we only separate the students whose parents have those specific levels of education, so bachelor's, associates, or some college, and we just want to see how those scores compare based on if they have taken test prep courses or if not. So what we do is we just we once again calculate the mean for each of the different features. So for example, if the parental influence is low, in the case of if they have an associate's degree or if they have no, or if they have some college, we want to compare that against maybe how do those students do compared to like students with the same level of parental education, but that they haven't taken test prep courses. So we're just looking for like, does the parental influence change like how well you do in school? And then we want to do the same thing, but in the case of the students that have a parent with a bachelor's degree, and we want to look at that. So what we do is we just sum up all of the different test scores for the four different conditions. So for example, we want to look at the students that are influenced by their parents who have a bachelor's degree, and we want to see how their test scores compared to students who aren't influenced by parents who have their bachelor's degree. And we also want to look at students whose parents have an associate's degree or equivalent that are influenced versus the students that aren't influenced whose parents have a associate's degree or equivalent. So then I just plotted this graph, which is just for illustration purposes. Again, in the real life or in the real world, you would just put these features and put these data into a model, and you would train it and see how it compares. But we can see that there are some differences in how these students perform in terms of their math score, their reading score, and their writing score. And obviously, this is a hypothetical. And when you create actual variables, or sorry, if you create actual features, then they'll really just depend on like the problem and the situation that you're faced in, and what kind of perspective you want to look at. In this case, we want to look at parental influence, and it really just depends on the problem and the data set. And one last thing I want to highlight is that for feature creation, it doesn't have to be just a qualitative value that like we decide on ourselves. So for example, we could have created another feature, and this could have been just called the cumulative test scores. So what we would do is we would just look at all of the labels of the reading score, the writing score, and the math score, and we just combine them into a weighted average, and we can just call that the student performance score in all three of their tests. And we can see that if we don't really care about like how students do in such a granular way and only looking at those three categories, if we just want to just kind of gauge in general how students do well in school, then we could just combine all of those three features into one, and we can call it the cumulative test score. And we can just use that feature instead, which will save on a lot more computational time. And I believe that is all. So if there are any questions, feel free to ask.